Okay, so let's evaluate the given integral by changing it to polar coordinates. So we have a double integral over a region R, sine x squared plus y squared dA, where our region R is the first quadrant between the circles with the center at the origin and radii 2 and 3. So if we can draw our region, it's honestly something that I would largely recommend, is to draw your region. This is going to be true for a lot of double integrals. In fact, most of double integrals, you have to draw your region, and it's super helpful to draw your region because it literally tells you, it tells you a lot of information that is very easy to look at and visualize and set up your integral based on. So highly recommended to draw it out. Now, the thing with this is, let me first draw it out, and then we'll discuss why polar coordinates is a good option for us. So both of these circles are centered at the origin, and one of them has a radius of 2, and the other one has a radius of 3. A radius of 2 is going to go 2 in each direction. Now, I'm only doing these two because we're only looking at the first quadrant. So we have a circle, not really a circle, it's like a quarter circle that we can draw like that. And then similarly we can draw our another circle, and this circle has a radius of 3. Now if we were to continue, it would obviously go all the way around, but we don't care about that. This is pretty much what you're looking for. Now the reason why we're using polar and we're not using rectangular, the way we could if we had like a rectangular region, is because whenever you have a non-rectangular region, a region that's has some curves to it, it's like a circle or some region that is very polar defined, if you will, then it's very easy for us to use polar. Whenever it's rectangular, or whenever we have when we have like a type 1 or type 2 region, which you might have seen. So it's like when you have a type 1 or type 2 region where you have one side being from constant to constant and the other one being like a function, something like this. We can also use the regular rectangular methods, but for something where it's very polar defined, like a circle, it's very easy for us to use polar coordinates instead. And oftentimes, this is just what we can use to simplify our process of calculation. So then it just, again, if it's like a circle or something, and that it's very easy to represent using polar, this is very easy. We could use polar for our double integral. So this here is when r equals to 3, converting it to polar, r equals to 3, and this is when r equals to 2. So double integral. Remember, your thetas are always going to go at the end, and the reason why is because they are going from constant to constant, and the r is going to go from it could go from a function to a function, or a constant to a function, something like that. And so that's why we always have our theta at the end. So theta equals, you can include this if you want. I will not, because typically you don't include it, but theta starts here, which is 0, and then it goes all the way here, which is pi over 2. So theta goes from 0 to pi over 2. That's half of pi, basically. And then what you want to do is you want to go specify your r. And the way you determine the r, I'm going to clear this up so we can get some space and or make it more clean. You start at the origin, and what you do is you keep on going until you enter your region. Now this is not your region. We've not entered your region because that's not your region. We're looking at it when it's between the two quarter circles. That's what it says here, where r is the region in the first quadrant between the circles. That's important, right? Between. So it's between these two circles here. This is the region. This is not the region itself that we're finding. We're not finding the volume, obviously, of this region. But what we're doing is we're looking at D, or D is this region right there, and then we're essentially integrating to find the volume over this region under our function sine x squared plus y squared. So this is your region. So you don't enter your region until you keep on going and you enter it here. That's when you immediately enter it. You enter it when r equals to 2, and then you keep going, and when you end at r equals to 3. So you go from 2 to 3. That's how you determine your region, or not your region. That's how you determine your r range, your r values. Then what you do is, it's very easy. You just rewrite this. So it's sine of, I'll write it as x squared plus y squared, and then we'll change this later. I like to, not forget about something very important, which is actually a Jacobian. But if you don't know what a Jacobian is, yeah, that's fine. Remember, whenever you have your dr d theta, this is something you won't forget to add, because you have to add it. You also have to add an r dr d theta. It's very important. This is your Jacobian. Basically, it's used to convert from xy to r theta, and you need this to convert. That's a Jacobian. You'll learn that. If you want to, you can learn that as well. You will learn that in the future. So it's just something. Now, obviously, this is like odd. Yeah, this is very odd. Why is x squared plus y squared here when we have everything in terms of r and theta? Well, because we haven't converted it yet. We have to convert everything in terms of r and theta. X squared plus y squared is equal to r squared. This is an important conversion that you need to know. So this can be written as r squared. X squared plus y squared is r squared. This is just r squared. So that's basically what you have. You have, just to rewrite it because it's all colorful now, 0 to pi over 2, 2 to 3, sine r times sine r squared. R, we don't need our r because we have it there. We just moved it, dr d theta. Now we can use the u sub. We can set u equals to r squared and du equals to 2r dr. So we end up getting, and actually here what we can do is we can split this into two integrals. So 0 to pi over 2 of 1 d theta times 2 to 3 of r sine r squared dr. This is equivalent, it's the same thing. So we can still use our u sub though. Our u sub is still useful. It's just useful down here now. And so just to move on, this is easy. That's just theta evaluated. So it's equal to theta evaluated from 0 to pi over 2. And then multiply that by whatever this becomes. No, actually not. Let me go step by step. So this is going to be 2 squared, which is 4, 3 squared, which is 9, r, well, obviously we need a 1/2 because we're inserting a 2 because we don't have that, so 1/2, and then we can insert a 2 so we don't change the value, and then 2r dr is du, so we can replace this with du, and then sine of r squared is just sine of u. That's what we end up with. This is all good now. Now we can go again, theta from pi over 2 to 0. I want to do these evaluations at the end, so that's why I'm just rewriting it. Times 1/2, and then we have integral of sine is not cosine, it's negative cosine of u evaluated from 4 to 9. So let's continue up here. So we end up getting theta from 0 to pi over 2 times 1/2 negative cosine of u 4 to 9. The integration itself shouldn't be too bad. For the most part, they won't be complicated because this is not really testing your ability to integrate. You should know how to integrate. This is testing your ability to do, set it up, mainly to set it up, really. So, and then so we have minus and then negative, so it's going to be positive, and then cosine of 4. So hopefully I didn't make any mistakes, but we end up getting pi over 4 times cosine of 4 minus cosine of 9. And I don't think cosine of 4 and cosine of 9 will give us nice values, so let's just leave it like that. So that's your answer. That represents the volume under the region, under the function sine of x squared plus y squared, which gives you like a region, a surface, I should say, under the surface over our region. That's what it gives you, the volume, and we're good.